What makes this terrifying is not its size alone. It is that we have seen something almost identical before. In 1859, a sunspot of nearly the same proportions unleashed what scientists now call the Carrington event, the most devastating solar storm in recorded human history. Telegraph lines caught fire. Operators were electrocuted at their stations. The night sky over the Caribbean glowed red with auroras that had no business being there. Now, 166 years later, we're staring at its twin. But here is what keeps scientists awake at night. In 1859, the world ran on steam and copper wire. Today, our civilization floats on satellites, pulses through fiber optic cables, and breathes through power grids that stretch across continents. A Carrington-class event striking Earth tomorrow would not just inconvenience us, it would erase the infrastructure of a modern life. The estimated damage exceeds $2 trillion. The blackouts could last not hours, not days, but years. And the sunspot that could trigger all of this is active right now, hurling plasma into space, building energy with every passing hour. By the time this documentary ends, you will understand exactly what we are facing, why the next few weeks matter more than any other moment in the last decade of solar observation, and what the scientific community is too afraid to say out loud. Before we begin, always remember to like this video. It tells your algorithm that you love these topics and that you want more content just like this. And if you enjoy our calming deep dives into the mysteries of the cosmos, do not forget to subscribe and hit that notification bell so you never miss an update. Now tell me in the comments, where are you listening from right now? What time is it there? And have you ever witnessed a solar storm or aurora in your lifetime? I'm always curious to hear your stories. Now let us step into the fire. The sun does not sleep. We think of our star as this constant, reliable presence, rising each morning and setting each evening with mechanical predictability. But that image is a comforting illusion. The reality is far more violent. Beneath that golden disk lies a churning ocean of plasma, a sphere of hydrogen and helium undergoing constant nuclear fusion, at temperatures exceeding 15 million degrees Celsius in its core. And on its surface, where temperatures drop to a mere 5,500 degrees, something strange emerges from time to time. Dark patches, cooler regions where intense magnetic field lines have become so concentrated, so tangled, that they actually inhibit the convective flow of heat from below. We call these sunspots, and they are the birthplaces of chaos. On November 28, 2025, something extraordinary rotated into view on the sun's eastern limb. Astronomers watching their monitors noticed a dark region emerging, but as hours passed, it became clear this was no ordinary sunspot. It kept coming and coming. It took more than 2 full days for the entire structure to rotate fully onto the Earth-facing side of the sun. When it finally revealed itself in its entirety, the scientific community fell silent. The complex, now designated AR4294-4296, spans an area so vast that NOAA was forced to split it into 3 separate numbered regions simply because their classification systems could not handle its scale. 130,000 kilometers of magnetically tortured solar surface, multiple cores, each one the size of Earth, and at its heart, a magnetic configuration so complex that scientists have given it the most dangerous designation possible, Beta Gamma Delta. Think about that for a moment. We have classification systems specifically designed to tell us how likely a sunspot is to explode, and this one has earned the highest threat level we can assign. Beta Gamma Delta means the magnetic field lines within this region are not merely complex, they are chaotically intertwined, twisted around each other like snakes fighting in a bag. When magnetic field lines of opposite polarity get forced together with this kind of intensity, they do not simply coexist, they annihilate each other. And when that annihilation occurs, the energy stored in those twisted fields gets released in a fraction of a second. The result is a solar flare, a burst of electromagnetic radiation so powerful it can cross 93 million miles of space and ionize Earth's upper atmosphere in just 8 minutes. But here is where things get truly unsettling. On December 1st, the sun did exactly what scientists feared it might. An X1.9 class solar flare erupted, not from AR4294 itself, but from a neighbouring region called AR4299 that had just rotated back into view. This was a region we had seen before, back in November, when it triggered stunning auroras visible across much of the northern hemisphere. Now it was back, and it announced its return with one of the most powerful flares we have seen this year. The explosion ionized the atmosphere over Australia and Southeast Asia, causing radio blackouts that affected aviation and maritime communications for approximately 30 minutes. Satellites detected the surge, Instruments on Earth confirm the disruption. And all of this was just the opening act. The real concern is what comes next. You see, solar flares are only half the story. When those magnetic field lines snap and reconnect, they do more than emit radiation. They can also hurl physical matter into space, billions of tons of charged particles, protons and electrons, traveling at speeds that can exceed 7 million kilometers per hour. We call these eruptions coronal mass ejections, CMEs, and they are the true harbingers of geomagnetic chaos. A flare reaches Earth in 8 minutes because it travels at the speed of light. A CME, being made of actual matter, takes longer, usually between 1 and 3 days, depending on its velocity. And when that wall of charged particles slams into Earth's magnetic field, it creates something called a geomagnetic storm. On December 6th, the Sun struck again. AR4294 produced an M8.1 flare, just shy of X-class. But this time the geometry was different. This time the explosion launched a full halo CME, meaning the ejection is heading straight for Earth. The velocity measurements are staggering, 1,143 kilometers per second. That is over 2.5 million miles per hour. NOAA has issued a G3 strong geomagnetic storm watch for December 9th. And as of this recording, that storm is either imminent or already beginning to interact with our planet's magnetosphere. Let that sink in. We are not discussing theoretical scenarios. We are not speculating about what might happen someday. This is happening right now. The CME is in transit, the sunspot complex remains active, and the magnetic configuration that could produce an even larger event is still intact, still pointed at Earth, still building energy. What fascinates and terrifies researchers in equal measure is the comparison being drawn between AR4294 and the sunspot that triggered the Carrington event. Richard Carrington was a British astronomer who, on September 1st, 1859, happened to be observing the Sun through his private telescope when he witnessed something no human had ever documented before. A brilliant white light flashed across the surface of a large sunspot group, intensified for approximately 5 minutes, and then faded. He had no idea what he was seeing. He rushed to find a witness, but by the time he returned, the phenomenon was already diminishing. What Carrington had observed was the first recorded solar flare in human history. 17 hours later, the sky caught fire. Auroras erupted across the planet, visible not just in the Arctic and Antarctic, but in Cuba, Hawaii, Colombia, even as far south as Santiago, Chile. In the Rocky Mountains of the American West, gold miners woke in the middle of the night, convinced it was dawn, and began preparing breakfast. In the northeastern United States, people reportedly read newspapers by the light of the aurora alone, but the beauty masked destruction. Telegraph systems, the most advanced technology of the era, went haywire. Operators reported receiving severe electric shocks. Machines sparked and smoked without any batteries connected. In several locations, telegraph paper caught fire spontaneously. The electromagnetic disturbance was so intense that it induced currents in every conductor it touched. Now look at the sunspot currently facing Earth. When spaceweather.com superimposed Carrington's original 1859 sketch over modern imagery of AR4294, the resemblance was immediate and alarming. The current complex covers approximately 90% of the area that Carrington's sunspot occupied. It displays the same multi-core structure, the same magnetic complexity, the same potential for catastrophic energy release. The main difference is that in 1859 the world depended on perhaps 100,000 miles of telegraph wire. Today we depend on 200,000 miles of high-voltage transmission lines, thousands of satellites, billions of internet-connected devices, and a global economy that would collapse within hours of losing electrical power. The question is no longer whether a Carrington-class event will happen again. The question is when. And looking at the solar surface right now, looking at the data streaming in from NASA's Solar Dynamics Observatory, from NOAA's GOES satellites, from amateur astronomers around the world photographing the sun through hydrogen alpha filters, the answer might be sooner than anyone wants to admit. But size alone does not determine whether a sunspot will erupt. The magnetic field configuration matters enormously. The rate at which new magnetic flux emerges from below the solar surface matters. The shear forces between regions of opposite polarity matter, and perhaps most importantly, chance matters. We have seen giant sunspots rotate across the face of the sun without producing a single significant flare. We have seen tiny, seemingly insignificant regions explode with X-class fury. The sun does not follow our predictions. It follows physics, and the physics of magnetic reconnection involves variables we cannot measure with perfect precision. What we can measure is probability. And right now, the probability assessments are sobering. NOAA's Space Weather Prediction Center has been issuing daily forecasts that place the chance of M-class flares at 70% and X-class flares at 15 to 20% for the period, while AR4294 remains on the Earth-facing disk. Those numbers might sound modest until you realize that we are talking about the potential for multiple major eruptions over a period of approximately 2 weeks. Each one is a roll of the dice. Each one could be the trigger for something far worse than what we experienced on December 1st or December 6th. And here is the detail that truly keeps solar physicists watching their instruments with nervous anticipation. The sunspot complex has been remarkably quiet considering its size. For 3 days straight, mathematical models showed a 30 to 70% probability of X-class flares, yet not a single M-class event occurred during that window. The region just sat there, absorbing energy, twisting its magnetic field lines tighter and tighter, like a coiled spring waiting to release. When a sunspot of this magnitude stays quiet for this long, it means one of two things. Either it is stabilizing and will rotate harmlessly off the western limb without incident, or it is storing energy for an explosion that will dwarf anything we have seen in years. There is no way to know which outcome awaits us, and that uncertainty is what makes the next several days so critical to monitor. 90% of a nightmare. When astronomers first began comparing the current sunspot complex to historical records, they reached for the most famous solar event in human memory. The Carrington event of 1859 has become the benchmark against which all extreme space weather is measured. It is the storm that proved the sun could reach out and touch our technology. It is the event that demonstrated in unmistakable terms that we are not isolated from our star. And now, 166 years later, we find ourselves staring at something hauntingly familiar. The measurements are striking. AR4294 through 4296, when analysed for total area coverage, spans approximately 2,300 millionths of the solar hemisphere. To put that in perspective, a millionth of the solar hemisphere is roughly equivalent to 3 million square kilometres, about the size of India. So we are talking about a dark region on the sun that, if transplanted to Earth, would cover most of a continent. This makes it one of the largest sunspot complexes observed in the 21st century, rivaled only by the infamous region 486 from October and November of 2003, which produced 2 of the most powerful solar flares ever recorded. But the comparison that has captured the imagination of both scientists and the public is the one to Richard Carrington's 1859 sunspot. When researchers at spaceweather.com overlaid Carrington's original hand-drawn sketch onto modern imagery of the current complex, the resemblance was immediate. The multi-lobe structure, the distribution of dark umbral cores surrounded by lighter penumbral regions, even the overall orientation on the solar disk, all of it echoed across more than a century and a half of time. The current complex covers approximately 90% of the area that Carrington documented. 90% of a nightmare. Think about what that means. We are not looking at a sunspot that is somewhat similar to the one that caused global technological disruption in 1859. We are looking at something that is, for all practical purposes, its near identical twin. The only significant difference in scale is that final 10%, a margin so slim that it provides almost no comfort whatsoever. The question that immediately arises is whether size alone determines the danger, and here this science becomes more nuanced than headlines might suggest. A large sunspot does not automatically produce large flares. The relationship between sunspot area and flare productivity is correlational, not deterministic. What matters far more than raw size is the magnetic complexity within the region, the rate at which new magnetic flux is emerging from beneath the solar surface, and the degree of shear between regions of opposite magnetic polarity. On all 3 of these metrics, AR4294 scores disturbingly high. The beta-gamma-delta classification it has received indicates the most complex possible magnetic configuration, one where positive and negative polarities are so thoroughly intermixed that the potential for violent reconnection events exists throughout the entire structure. New flux has been observed emerging continuously since the region first rotated into view, adding energy to an already stressed system. And the shear measurements, which track how much the magnetic field lines are being twisted and displaced from their equilibrium positions, are among the highest recorded for any sunspot this solar cycle. What we are witnessing is not merely a large sunspot. We are witnessing a magnetically loaded weapon pointed at Earth. The Carrington event itself offers a glimpse of what such a weapon can do when it fires. On September 1st, 1859, Carrington observed what he described as 2 patches of intensely bright and white light breaking out on the solar surface. The phenomenon lasted approximately 5 minutes before fading. He had no framework for understanding what he had seen. The concept of a solar flare did not yet exist. But he was methodical enough to record the exact time and position of the event, documentation that would prove invaluable in the decades to come. What Carrington witnessed was the release of energy that had been building in the twisted magnetic fields of that enormous sunspot. When field lines of opposite polarity are forced together, they can undergo a process called magnetic reconnection, where the field geometry fundamentally restructures itself into a lower energy state. The difference between the initial and final energy states is released instantaneously, producing electromagnetic radiation across the entire spectrum, from radio waves through visible light and ultraviolet, all the way to X-rays and gamma rays. The 1859 event is estimated to have been an X-45 class flare, a magnitude that almost defies comprehension. For reference, the most powerful flare recorded by modern instruments was approximately X-28 during the Halloween storms of 2003, and even that measurement is uncertain because it saturated the detectors. An X-45 flare would release roughly twice as much energy. It would ionize Earth's dayside atmosphere so thoroughly that high-frequency radio communication would be impossible for hours. The radiation pulse would arrive at Earth in 8 minutes, travelling at the speed of light, and there would be no practical way to prepare for its effects. But the flare itself, as dramatic as it was, caused only temporary disruption. The real damage came from what followed. The same magnetic reconnection event that produces a solar flare can also accelerate billions of tons of solar plasma to enormous velocities, launching it into interplanetary space as a coronal mass ejection. The Carrington event CME was exceptionally fast. It reached Earth in just 17.6 hours, a journey that typically takes 2 to 3 days. Researchers believe this remarkable speed was possible because a previous CME, launched a few days earlier, had cleared the ambient solar wind out of the way, creating a kind of vacuum tunnel through which the September 1st ejection could race unimpeded. When that wall of magnetized plasma struck Earth's magnetic field, it compressed the magnetosphere and triggered the most intense geomagnetic storm ever recorded. The DST index, which measures the strength of geomagnetic disturbances, plunged to an estimated negative 1,700 nanoteslas. Modern severe storms typically bottom out around negative 200 to negative 300. The Carrington event was roughly 5 to 6 times more intense than anything we've experienced in the space age. The auroral displays that resulted from this collision were unlike anything in living memory. Normally, auroras are confined to high latitudes, visible from places like Alaska, Scandinavia, and Antarctica. During the Carrington event, the auroral oval expanded so dramatically that the northern lights were seen in Cuba, Jamaica, and Hawaii. The southern lights reached Colombia and central Chile. In both hemispheres, the displays were described in terms that border on the apocalyptic. Blood-red curtains of light rippled across the sky. Pulsing green and violet bands stretched from horizon to horizon. The illumination was so bright that people could read newspapers outdoors at midnight. For those who did not understand what they were witnessing, the spectacle must have been terrifying. Religious interpretations were common. Some believed they were seeing the end times, others thought the sky itself was on fire. But beneath the celestial beauty, a more practical crisis was unfolding. Telegraph systems around the world began to fail. Operators reported sparks shooting from their equipment. Some received painful electric shocks merely by touching the metal components of their stations. In several documented cases, telegraph paper caught fire and burned. The most remarkable reports, however, described something that seemed impossible. Operators who disconnected their batteries found that their equipment continued to work, powered entirely by the auroral currents surging through the wires. Messages were sent between Boston and Portland, Maine, using nothing but the electricity being induced by the geomagnetic storm. This was humanity's first direct encounter with the phenomenon we now call geomagnetically induced currents, or GICs. When Earth's magnetic field fluctuates rapidly, as it does during a geomagnetic storm, those fluctuations induce electric fields in the ground itself. Any long conductor, whether a telegraph wire, a power line, or a pipeline, will pick up these induced currents and allow them to flow. In 1859, the only long conductors in existence were telegraph wires, so the damage was limited to that technology. But the principle demonstrated in that event applies equally well to the infrastructure of the modern world. Today, we have approximately 200,000 miles of high-voltage transmission lines crisscrossing North America alone. We have natural gas pipelines stretching thousands of kilometers. We have undersea cables carrying internet traffic between continents. Every single one of these systems is vulnerable to the same phenomenon that set telegraph stations ablaze in 1859. The difference is one of scale. A Carrington-level event today would not merely disrupt communications for a few hours, it would threaten the foundations of technological civilization. The sunspot we're watching right now has 90% of the physical characteristics that produced that historic catastrophe. It has already demonstrated its capacity for violence, with the X1.9 flare on December 1st and the M8.1 flare on December 6th. The CME launched by that second event is currently in transit, expected to arrive within hours of this recording. And through it all, the primary complex AR4294 has remained eerily quiet, storing energy rather than releasing it. Amateur astronomer Patricio Leon, who's been tracking this region since it first appeared, noted something remarkable about its emergence. The sunspot complex required more than 2 full days to rotate entirely past the eastern limb of the Sun. 2 days. For context, the Sun rotates approximately 13 degrees per day as seen from Earth. A structure that takes 2 days to fully emerge must therefore span at least 26 degrees of solar longitude, an enormous arc that testifies to the sheer physical scale of what we're dealing with. Leon also noted the delta magnetic component, the most dangerous classification, and observed that now that the region is fully Earth-facing, we are exposed to whatever activity it may produce. There is no longer any buffer. The barrel of the gun, if you will pardon the metaphor, is pointed directly at us. NOAA has divided the complex into 3 separate numbered regions: AR4294, AR4296, and AR4298, because their cataloguing systems were not designed to handle a single structure of this magnitude. This administrative decision underscores just how exceptional the current situation is. We are not dealing with routine solar activity. We are dealing with something that pushes against the limits of our classification frameworks. The comparison to the Carrington event is not mere sensationalism. It is a sober recognition that the Sun is capable of producing storms that would fundamentally alter human society, and that the current solar configuration bears an uncomfortable resemblance to the conditions that preceded the most extreme such storm on record. 90% of a nightmare is still close enough to keep scientists watching their screens with growing unease. And here is the detail that transforms unease into genuine concern. The Carrington event occurred during solar cycle 10, near the solar maximum of 1860. We are currently in solar cycle 25, and although NOAA's official position is that the cycle peaked sometime in 2024, the Sun has not received that memo. Activity remains elevated, sunspot counts exceeded predictions throughout most of this cycle, and the emergence of AR4294 during what should be the declining phase of solar maximum suggests that we may not have seen the last of the fireworks. The next few days will reveal whether this sunspot complex follows the path of its 1859 predecessor or fades quietly as it rotates toward the western limb. Either outcome is possible, but the mere existence of this region, its scale, its magnetic complexity, and its obvious family resemblance to history's most destructive solar storm demands that we pay attention. 90% of a nightmare is close enough to count. The day the sun set, telegraph wires on fire. The morning of September 1st, 1859 began like any other for Richard Christopher Carrington. The 33-year-old English astronomer had established a private observatory near Redhill in Surrey, where he dedicated himself to the systematic study of sunspots. He was meticulous, methodical, and possessed of the patience required to spend hours each day projecting the solar image through his telescope and carefully sketching what he observed. He had no idea that this particular morning would immortalize his name in the annals of science. At approximately 11:18 in the morning local time, Carrington was engaged in his usual routine, documenting a large group of sunspots that had been visible for several days. The group was impressive, covering an area easily visible through properly filtered optics, but there was nothing about it that suggested impending violence. Then, without warning, 2 patches of intensely bright and white light erupted from the dark cores of the sunspot group. Carrington later described the phenomenon as appearing like 2 beads of brilliant white, far exceeding the luminosity of the surrounding solar surface. He was stunned. In all his years of solar observation, he had never witnessed anything like it. His first instinct was scientific. He needed a witness to confirm what he was seeing. He rushed from his observing chair to find someone, anyone, who could corroborate this extraordinary event. By the time he returned, less than 60 seconds later, the phenomenon was already fading. The 2 bright points had expanded slightly and diminished considerably in intensity. Within 5 minutes, they had vanished entirely, leaving behind the same sunspot group that had been there before, apparently unchanged. But Carrington knew he had seen something unprecedented. He recorded the precise time, the exact position on the solar disk, and every detail he could recall about the appearance and evolution of the light. What Carrington did not know, could not have known, was that he had just witnessed the first documented solar flare in human history. The concept did not exist. The mechanism was unknown. The connection between solar events and terrestrial effects was purely speculative. But in that moment, watching those 2 points of white fire fade into the ordinary brightness of the sun, Carrington became the first human being to directly observe the phenomenon that would, one day, threaten to bring down civilization. He was not the only observer that morning. Richard Hodgson, another English astronomer, was independently monitoring the sun from a different location and witnessed the same event. The two men would later publish their observations side by side in the monthly notices of the Royal Astronomical Society, providing crucial corroboration that the event was real and not an artifact of instrumentation or imagination. 17 hours and 40 minutes after Carrington watched the white light fade, the consequences of what he had seen arrived at Earth. The first indication that something unusual was happening came from compass needles. Magnetometers, instruments designed to measure the strength and direction of Earth's magnetic field, began behaving erratically. At the Kew Observatory outside London, Scottish physicist Balfour Stewart was monitoring a recording magnetometer when the needles suddenly pinned against their stops. The fluctuations were so extreme that the instruments could not track them. Something was disturbing Earth's magnetic field on a scale never before recorded. Then the sky began to glow. Auroras are nothing new to observers at high latitudes. The dance of coloured light across polar skies has been documented for millennia, woven into mythology and folklore from Scandinavia to northern Canada. But what appeared on the night of September 1st and continued through September 2nd was not a typical auroral display. It was a global phenomenon, visible from locations where auroras had never been seen before and might never be seen again in a human lifetime. In the American West, gold miners working in the Rocky Mountains were jolted awake by the strange illumination. Convinced that dawn had arrived early, they rose from their bedrolls and began preparing breakfast, only to discover that it was still the middle of the night. The sky blazed with crimson and green light, bright enough to cast, shadows bright enough to read by. Similar reports emerged from across the northern and southern hemispheres. In Queensland, Australia, observers noted brilliant red glows on the horizon. In Chile, astronomers documented auroras extending far north of their normal range. In the Caribbean, populations who had never seen such phenomena stared skyward in wonder and terror. The New York Times dispatched reporters to cover the strange event, and their accounts paint a vivid picture of public reaction. In cities across the northeastern United States, people gathered in streets and parks to watch the celestial display. Some believed they were witnessing a sign from God. Others feared it heralded the end of the world. A few, more scientifically inclined, suspected that something unusual was happening on the sun. But while millions of eyes gazed upward in amazement, a quieter crisis was unfolding in telegraph offices around the planet. The telegraph system of 1859 represented the cutting edge of human technology. First demonstrated commercially in the 1840s, it had expanded with remarkable speed. By the time of the Carrington event, approximately 100,000 miles of telegraph wire crisscrossed Europe and North America, connecting cities, coordinating commerce, and transmitting news at speeds that had seemed impossible just a generation earlier. Journalists called it the Victorian Internet, and the comparison was apt. For the first time in human history, information could travel faster than a horse or a ship. On the night of September 1st, this revolutionary network began to fail. The problem started subtly. Operators noticed that their equipment was behaving strangely, producing erratic signals and requiring unusual adjustments to maintain communication. As the auroral display intensified, so did the interference. Sparks began jumping from telegraph keys and sounder mechanisms. Operators reported painful electric shocks when they touched metal components. In several offices, the sparks were intense enough to ignite the paper tape used to record incoming messages. Small fires broke out at telegraph stations from Boston to Brussels. The American Telegraph Company office in Boston provides one of the best documented accounts of what happened. Operators arrived for their morning shift on September 2nd to find that sending and receiving messages was nearly impossible. The instruments fluctuated wildly, signals were garbled beyond recognition, and the equipment seemed to have developed a mind of its own. After several hours of frustration, an operator made a discovery that seemed to violate everything known about electrical engineering. He disconnected the batteries. In normal operation, telegraph systems required batteries to generate the electrical current that carried signals through the wires. Without batteries, there should have been no current, no signal, no communication. But when the Boston operator, removed his batteries from the circuit, the equipment continued to function. Messages were successfully exchanged between Boston and Portland, Maine, using nothing but the current being induced in the wires by the geomagnetic storm itself. The aurora was powering the telegraph. This phenomenon, while appearing almost magical to 19th century operators, has a straightforward physical explanation. When Earth's magnetic field fluctuates rapidly, as it does during a severe geomagnetic storm, those fluctuations induce electric fields in the crust of the planet. Any conductive material in contact with the ground, such as the grounded telegraph wires of the era, will pick up these induced electric fields and allow current to flow. The longer the conductor, the greater the voltage that accumulates along its length. Telegraph lines, stretching hundreds of miles between stations, acted as enormous antennas, collecting the auroral electricity and funneling it into equipment designed to operate on tiny battery voltages. The same effect that allowed operators to send messages without batteries also produced the sparks, shocks, and fires that plagued the system. The induced currents were not stable or controlled. They fluctuated with the varying intensity of the geomagnetic storm, surging and ebbing unpredictably. Equipment designed for milliamp currents found itself conducting tens or even hundreds of times that amount. Insulation failed, contacts overheated, paper ignited. Reports from telegraph offices around the world tell similar stories. In Philadelphia, operators observed sparks showering from their instruments and described fantastical and unreadable messages appearing on their equipment. In Washington, an operator named Frederick Royce received a severe electric shock that stunned him for an instant, as reported in contemporary newspaper accounts. In Victoria, Australia, the General Superintendent of Electric Telegraph, Samuel McGowan, compiled a formal report for the Victorian Parliament documenting the interruptions to telegraphic communication throughout the colony. The disruption lasted approximately 2 days, coinciding with the duration of the most intense geomagnetic disturbance. As the storm subsided and Earth's magnetic field returned to normal, telegraph operations gradually resumed. Damaged equipment was repaired or replaced. The fires had been small enough to extinguish, without major property loss. By the end of the first week of September, the Victorian internet was back online, and for most people, the strange events were already fading into memory. But for a handful of scientists, the Carrington event raised profound questions. Richard Carrington himself noted the coincidence between the solar flare he had observed and the geomagnetic storm that followed, but he was cautious about claiming a direct causal connection. "One swallow does not make a summer," he wrote, acknowledging that correlation does not prove causation. Yet the net timing was suggestive. A brilliant eruption on the Sun followed less than 18 hours later by the most intense geomagnetic disturbance in recorded history. Could the Sun truly reach out and touch the Earth in this way? It would take decades of additional research to confirm what Carrington suspected. The connection between solar flares, coronal mass ejections, and geomagnetic storms is now well established. We understand the physics. We can predict, with reasonable accuracy, when a solar storm will arrive and how intense it might be. What we cannot do, despite all our technological advancement, is prevent the consequences. The telegraph wires of 1859 have been replaced by power grids and fibre optic cables.